Yeah, last week, this is what we started with. We started with clay clarifying and cross filtration system, right? Okay. Now, I think we stopped at this place. Yeah, we stopped at Darcy law, and though I said this one is not important, but it's important, we need to just go through it. That's estimating flux in filtration filtration process. Estimating flux in filtration process. What is flux? Flux is the rate at which fluid passes through a membrane. Please listen. Are we ready? Yes. So flux is the rate at which fluid passes through a membrane filter per unit area. So we use these parameters to determine the performance of a filtration system. So, and there are different factors that affect membrane flux. So we said flux is the rate at which fluid passes through the what? Membrane filter, or through the filter. So when we have higher flux, what do you think will happen? If the rate at which fluid passes through a filter is called flux, so if we have higher flux, what do you think will happen to the filtration rate? It will be higher. So when the flux is lower, then the filtration rate is what? Is lower. You now see the reason why we use J flux to determine the performance of a membrane. And there are different factors that affect J flux. The first factor is transmembrane pressure. That's the pressure applied. Membrane resistance, viscosity of fluid, concentration, polarization. These are some of the factors that affect J flux. And on this, I can ask you a question relating to this, that you have a membrane filter, and you discover that the performance of that membrane filter is low. So how do you, or let's just say the performance or the efficiency of that membrane filter is low. Now, what are some of the factors to consider in order to know what actually happened in that membrane filter? So the first thing is that we look at what? Transmembrane pressure. So if the transmembrane pressure is high, then we know that what? Is low rather. If the transmembrane pressure is low, then we know that J flux, that is the reason why we have what? Lower membrane, what's the name? Lower membrane, lower J flux. Then we look at membrane resistance. Do we have fouling or scaling? Fouling is when you have the surface of a filter being clogged by some of the particles. So, and we have viscosity of fluid. So the higher viscosity, the lower the flux. It's more like when you have something that is thick, it will be difficult to push. So the last one is concentration polarization. When there is a buildup of rejected solids near the membrane, it decreases the flux. And now we have a formula to determine the membrane flux, and this is QP divided by area. Very easy. So QP is a permeate flow rate, that is the fit rate coming out. And so sorry, you went to that place, right? Or you are just coming?
No, our bus are late, so that's why we...
Okay. Just want to be sure because there is an issue with the location. So A is the area of the membrane. So that is that about that. So this is just the parameters we use in determining the membrane flux. Now, we mentioned that there are different factors that could be responsible for a lower membrane flux. We mentioned that transmembrane pressure, when it is low, it can actually affect the rate at which the fluid passes through the filter. So transmembrane pressure is the driving force that pushes fluid through a membrane in a filtration process. So this is the pressure difference across the membrane that influences the filtration rate. Now, what are the roles of transmembrane pressure? When we have higher transmembrane pressure, the filtration rate, so higher transmembrane pressure increases filtration rate. We've mentioned it, right? But may actually cause fouling when the pressure is too high. Then, when we have low transmembrane pressure, it may actually lead to what? Inefficient what? Separation, because the filtration rate will be what? Will be low. And one of the most important parameters, hello, when we are in my class, hello, please, you're just coming. Don't disturb us. So, whenever you want to increase the performance of any membrane, and you want to increase like the performance of, you want to optimize the transmembrane pressure, then you have to maximize the flux, and it helps in maximizing the flux and the membrane lifespan. An example is this: when the membrane pressure is too high, there will be more pressure on that filter, right? And when there is more pressure, what happens? The lifespan of that filter will reduce, because it can cause tear and wear, and at the end of the day, the membrane may tear or crack or anything. So when we and that's the reason why we need to optimize the transmembrane pressure. What is the meaning of optimization? Optimization has to do with using the right pressure, the right parameter pressure. I mean, it will not be too low and it will not be too high. So that's optimizing. So we need to optimize the transmembrane pressure for us to get a good filtration rate. And we have a formula for transmembrane pressure. Transmembrane pressure equals P inlet, that is the pressure of the inlet plus the pressure of the outlet divided by 2 minus P permeate. What is permeate? Permeate is just the filtrate that is coming out, right? Then we have retentate. Retentate is the residue that is on top. That's what I'm saying. So let's say we have this. So, and then we have the underflow. So this one we call it retentate. And this one we call it what? Permeate. It's more or less like same filtrate. The reason why we are using this one is because we have different kind of filter. We have membrane-free filter also. So membrane filter works according to the principle of membrane and also the principle of filtration. So we have the P inlet and we have the P outlet. When we have pressure, the inlet pressure and outlet pressure, which one do you think we have the higher intensity? Is it the outlet or the inlet? Inlet, because that is where the pressure is coming from. Then we have the pressure of the permeate also. That is the rate at which the liquid is dropping. Pum, 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 pum. If it is far, zzz. If it is small, pum, 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 pum. You understand? So that is the pressure of the permeate. So note this formula. Now, membrane resistance. Now, this is the second. No, I told you there are different parameters we can use. See this. You remember this? Aha. So there are different parameters you can use in determining the performance of a membrane filter, of a filter. And one of it is what? Transmembrane pressure. We've dealt with that, all right? With the formula. The next one is the membrane resistance. So for membrane resistance, this is the formula for membrane resistance. J equals to TMP. What is TMP? Transmembrane pressure. Divided by what? Fluid viscosity into Rm. Rm is the membrane resistance. That's what we're talking about. Then we have Rf. That is fouling resistance due to deposits on the membrane. So now, there are different for membrane resistance. There are different factors affecting membrane resistance. One of it is what? membrane pore size. Next one is what? Membrane fouling. And the next one is what? The fluid properties. You need to understand this concept because membrane resistance is just the opposition that a membrane provides to the flow of liquid during filtration. Let me give you an example. Have you ever experienced rain falling and you have your umbrella like this, right? You have the umbrella like this. Let's say this is Jose, right? Handling the umbrella, right? Which are flowing down. So I guess this is an example. You know now, you have what? Rainwater falling on you, right? But you already have what? You already have an umbrella, right? What happened? This is the inlet pressure, right? But have you ever experienced when it is raining, you will hear one sound, pa, 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 pa. As if this one is what? Is rejecting the water. So that is more like the pressure exerted by what? By this membrane. Let's say this is just the membrane, right? So this one also has its own pressure also. And for this one now, we call this a umbrella resistance, right? So for this one now, we have the what? Membrane resistance. And there's different factors. Okay, no, before we move into that, what is the implication of having higher membrane resistance? Like, membrane resistance is the opposition that a membrane provides to the flow of liquid during filtration. It affects the flux and overall filtration efficiency.
The umbrella, you said it's water resistance, the particles, fluid viscosity, the fluid we are putting on the umbrella.
No, I'm just using as an example.
There is no permission, so.
No, there's no permission. I just want to use that one to explain the resistance, when something is resisting. Because even though there is what? There is hole inside.
Okay.
Don't forget, everywhere is not covered by hole. We still have, this is what I'm saying. Let's say this is the hole. We still have all these spaces, right? So those are the spaces that will offer resistance, right? And most times, it's also dependent on the size of that pore size, the pore size. If the pore size is what? Okay, let me give you an example. Don't worry. I'll give another example. Has it ever happened to you that maybe you bought liquid bathing soap, right? So you have the container, small container already, and you like that container, it's beautiful. So you have another one you bought, but the other one is you've exhausted it, and you want to pour inside. Pour the, what's the name? Pour the detergent or the soap inside. Even though it's possible that this container is not filled up, but you are pouring inside this one because of, let's say, smaller hole. You will discover that at times it will be pouring outside. Not because this one is filled up, but it's because there is what? The hole is smaller. Do you understand that scenario? Yes. So the fact that you have a hole, you understand, is not an indication that this hole cannot offer resistance. Because if the rate of pouring it here, because it happened to me yesterday and I remember filtration. That, okay, let's say the rate, so what I do most of the time is that I will reduce the rate at which I will pouring small to accommodate this hole. Do you understand? So that's what you are saying, that in membrane or in filtration system, we have membrane flux, which is the rate at which the fluid is flowing through the filter, right? And we have membrane filter also. So filter is saying, okay, come on, I can accommodate your force, right? So as you are giving me more of those, what's the name? The liquid, there is rejecting it and taking some. So that is what? That is membrane resistance. And what are different factors that affect the membrane resistance? Because the higher the resistance, when you look at that equation, J is the flux, right? So that it is inversely proportional. So it means if the membrane flux is higher, flux, not pressure now. If the membrane flux is higher, what happens? The resistance is what? Lower. And when you look at this TMP2. If you want to see what is the difference between TMP, J mu rho. So it means the pressure is directly proportional. The higher the pressure, the higher the resistance. Do you understand it now? So that is the reason why we need mathematical equation to be able to understand how the process works. Do you understand now? So the first factor that affects membrane resistance is membrane pore size. The next one is what? Membrane fouling. The next one is what? Fluid property. Is it of high viscosity or low viscosity? So now, reducing fouling and cleaning membrane help maintain optimal resistance and improve filtration efficiency. This alone, I can ask you a question based on this. Or understand the concept, I can give you a scenario in which we have fouling and scaling, and we need to use backwashing or whatever it is to clean that surface. Then I can ask you, what are different factors that could be responsible for what? I mean, what can we do to reduce the fouling and something? So it will build around this. So just understand the concept, right? So that is that about membrane resistance. So that's the second factor that affects what's the name? That's the second factor that affects flux, J flux in membrane filter. Let's look at this. A dairy processing plant uses cross-flow filtration to concentrate whey protein from raw whey. The system operates with a transmembrane pressure of this TMP of 2.5 bar, a membrane resistance RM of 5 times 10 raised to the power 12, and a fluid viscosity of this. However, after several hours of operation, fouling occurs due to what? Protein aggregation, adding a fouling resistance RF of this. So using Darcy law, calculate the permeate flux in liter per meter squared hour and analyze the impact of fouling on the system performance. Now, we are asked to calculate what? Permeate flux. So the first thing to do is that when you have questions like this, I don't like the way you always answer my question. The first thing is that you need to write out all the given values. That will give you an inkling of the next formula to use. You have a question? Okay. Now, the first thing is that we have the TMP to be 2.5 bar, right? And then don't forget, you don't need to cram all this equation. I will give you a list of equations. So I won't tell you what it is, but at least once you read, you know what those equations is for. And we have, so it's in 2.5 bar, so we need to convert bar to Pascal or Newton per meter square, whatever it is. Then we have the membrane resistance to be Rm, right, given. Then we have the fouling resistance to be Rf, and we have the fluid viscosity to be 0.01 Pascal. So from this formula, we need to get the total resistance. There are two resistance. The first resistance is the membrane resistance and fouling resistance. What is fouling resistance? Let's say at the end of the day, this membrane is offering a resistance. The same thing, the accumulation of small particles that is clogging the surface is also offering resistance. So we need to get the two resistance, Rm plus Rf, right? So that's how we got this one. Then we can calculate the permeate flux to be this. Then is a meter per second. We have to calculate is what? Liter per meter squared. And that's that about that. Then lest I forget, your question will be loaded. What I mean by loaded is that you have enough question but little time to do it. So please make sure you read very well. I know what I'm saying. I don't want anyone of you to fail, but it's better because now we have a standard we need to maintain, and there will be a standard that will check whatever we do. So don't expect something too cheap, right? Just make sure everything I tell you in class you understand the concept. Then later we have time to treat different tutorial questions. So from there, you know what is coming out. So whatever you want to give me, make sure it's something that makes sense, right? My question is not too difficult, but it will be difficult for you if you don't understand what we are doing in class. It will be more practical and practical reality and something of that nature. So please listen and listen well. So now, this next question says, calculate the permit flux. So we already have that, right? And the next one says, analyze the impact of fouling on the system performance. How do we do that? Now, analysis of fouling impact initially. If there were no fouling resistance, that is RF equals to 0. So what we are saying in essence is that we know there will be accumulation of what? Of the droplet, right? That will block the surface, at least some of the surface. So what is the impact of that fouling on the performance? That's what we are talking about. Now, the first thing we do is that we will check if there is no fouling. You know there was fouling before that we calculated, right? That was the reason why we said, this is what I'm saying. Now, it's more or less like we calculated RM, RF, that's the total resistance, right? Now we want to see what will be the impact of that fouling. And how do we get the impact? It's more or less like when you are conducting an experiment and you have black solution without anything, because you want to show what is the difference between this and this. It's more like you have water without milk and you have milk without water, and somebody is asking you that what is the impact of adding milk inside water. You won't know the impact of adding milk inside water until you have water alone and you have milk with water. So this is what I'm saying. Now, we want to see what is the impact of fouling, that is when we have our surface being blocked, the surface of the filtration system being blocked. What is the impact of that on the performance? So you won't know the impact until you remove resistance. So we now assume that there is no resistance. Do you understand? So we assume that RF equals what? 0. So we will now see the J flux. So when without resistance is what? 180 liter per. It means 180 liter will pass through the membrane per meter squared without fouling. But you remember the one we calculated before with fouling? We got it to be 120 what? 128. It means when you subtract 128 from what? 180, it means there is what? Fouling has reduced the flux from 180 to 128.5. So about 28.5% drop in the performance. Do you understand now? Yes. Expect something like this. So, and the next question says, the impact, analyze the impact of the fouling on the performance. So now, it says, okay, this demonstrates how protein buildup in wave filtration significantly reduce efficiency, requiring cleaning or membrane maintenance to Now, I cannot add another question and say, how can you restore optimal, how can you restore the process to optimal operation after the fouling? Very simple. Cleaning or by conducting membrane maintenance. So that's full question. Is that clear now? So if I will give you something like this, I will start from all the, that was the reason I said the question will be loaded. You remember all the questions I asked you from here? Filter head, everything. That will be a single question. All this filter head, blah, blah. All this. So it will be a full question. It will be question, part A. It's not, they are not questions that you cannot solve. But if you don't prepare very well, you won't have time to solve, to finish it up. So that is the reason you are a master student, right? So you need time to think and to what? To be able to give me a solution. But beside this, just understand the concepts of this. And that's the most important thing to me now. So that's what we did last week. So today, we won't be able to go through the Stokes law because this Stokes law is particle settling So we deal with this under sedimentation. So there is no need of going through this so that it will not be repetition. So today will be, I'm coming. So we start hydroclone or hydrocyclone. Do we have any question before we move to this? Any question, please? Please, if you have any question, please don't be shy. At least I'm free enough with you, right? So please, if you have any question, let me know. Su what? Suchaya. Do you understand? Okay. So let's look at hydrocyclone. What is hydrocyclone? This is a form of separation hydrocyclone is a form of separation. It's used in chemical engineering, and the reason why I'm giving you all this is because in your design projects, so it's possible you have, we have separation process, integrated separation process. So it's possible you have 3 or 4 separation units matched together. So maybe you have like you have your sedimentation matched with cyclone, matched with this. So you need to understand the principle behind each, and all this process calculation you need to apply it in that design project. But when it get to that time, I will tell you what to do. But just understand all the major concepts here, then the better for your projects. Who is Pratam Kumar? Okay, you sent to Amit, right?
Sorry?
You are the one that sent to Amit? You are working on DNA, or?
Yeah.
Okay. So I'm your supervisor now?
Yeah.
So we need to maybe have a meeting together, because he told me about your matter and I said I would take it up.
Okay.
Who was your supervisor before?
Kyriakos.
Oh, Kyriakos. All right, I will take it up, right? Okay, now, overview of a cyclone. A cyclonic separation is a method of removing particles from an air, gas, or liquid stream without the use of filter. Through vortex separation, rotational effect and gravity are used to separate mixture of solids and fluid. So the method can be used to separate fine droplets of liquid from a gaseous stream. One important merit of this separation process is that it is less expensive compared to filtration process, right? And most times we use cyclonic separation before moving to filtration process. Reason is that majority of our particles will have been removed using cyclonic separation, and by the time we pass it through filtration system, we have no need to do too much maintenance on the filter. So that is the reason why most of the time when we have an integrated system, we can actually add cyclonic separation to it for optimal performance. So cyclonic separation is a separation where we remove particulate from air or gas or liquid stream without the use of filter. So the most common form of particulate removal is spun rapidly. It's more or less, I don't know, how many of you have seen in a construction site, you always have something like this. Have you seen something like that? Though it's just similar, but it's not what you want. But it's more or less like this, more or less like in a conical form like this, right? And it will be rolling like this. I think they use it for mixing concrete, right? So that is one, by the way, but I don't think it's not the same, but at least we can use that as an example. So for this, what's the name? This one will be moving like this. And in that process, there will be separation. And because the diameter is not the same, the diameter reduces down. So the force up will be different from the force down. Right? So now, the most common form of particulate, okay, now, heavier particle is collected on the outside of the separator by centrifugal force, where it is collected and removed. They create a dual fortes to separate quartz from what? Fine dust. In most instances, when we have granular particles, maybe in sugar production, granular particles and smaller particles, we can actually use it to separate fine particles from what? From bigger particles. So the main fortes spiral downward and carries most of the quartz dust particles. So the inner vortex creates near. So what is happening here is that inside this one now, we have something that is moving, just like this one may be stationary. That is why it is different from the one in construction sites. So it will be stationary like this, but it is inside. It's more or less like you have something like this. Right? So here, so this one might be stationary, but it is inside here. That will be what? That will be moving. Right? So it's more or less like if you have ever seen someone who is let me use an example. If you ever seen which example can I use? Okay, grinder. A grinder outside will be what? Stationary, but something is moving inside. So a cylinder is moving inside. A cylinder is moving inside, while the outer part is what? Is stationary. Exactly. So for this one now, we have a dual fortes. A dual fortes from the inlet. This is the inlet. And this is the what? Underflow. That's the outlet. Then we have the overflow. So this is product 1, product 2, but this is the inlet. So the one that is heavier will be collected and removed from, it depends, the denser one. You know, oil and water, between oil and water, which one is denser?
Oil.
Is oil denser than water, or water denser than oil?
Water.
Water, right? So the heavier one will be collected at the underflow, while the what? Lesser one will be collected up. So this is a mixture of liquid. We can use it for a mixture of liquid. That's one good thing about it. You know, for filtration system, it's only solid liquid, right? But this one we can use it for a mixture of liquid and gas and liquid, solid and solid. You see why it is more economical than filtration system to a larger extent.
For liquid and gas, when we want to separate the liquid from the gas, so liquid will be on the outer side?
No, will be from here.
Okay, because the liquid.
And this one, the less dense will be separated from the up. Just know it here that whatever you are separating, the denser one will be from here, and the less dense will be from here. And this is your inlet. We have different cone 1 and cone 2. So both of them will be having dual fortes, more or less like at the same time for separation. Then the inner vortex create near the bottom of the cyclone, spiral upward and carry fine dust up like this. So I've carried the fine dust up like this. So that is just the working principle. Let's look at this. Okay, this is one type of come in place. Okay, that is one type of industrial cyclone. So let's look at different components in a cyclone. We have the first one is vortex finder. This is just a central tube that extends into the body of what? The cyclone. It's more like when you have a grinder, you know, if you have normal grinder for grinding pepper, there's something you normally remove from the top, right? So without removing the cap, you can actually introduce anything inside. So if you are the one that likes putting maybe sugar when you are blending, or maybe you want to put like if you want to prepare soup, most of the time I like blending my spices with what you call it. So the same thing applicable. So something from the top here is the what? The vortex finder. So the next one is that we have tangential inlet ducts also. So that one is the entry point for the fluid containing particle. That's for introducing the feed. And it's key to creating the centrifugal force necessary for particle separation. Then, what are the principles of operation in a cyclone? The air or vapor containing particles material is forced into or along the tangential axis like this. This is for solid air. And now when we say tangential, that is at 90 degrees, right? So the centrifugal force causes the particles to what? To migrate to the outside of the chamber. So here they fall down to the bottom of the cyclone by what? Gravity. So we collect the particulate at the exits. So that is through the outer one. So the more dense will be collected here, while the less dense will be collected up. So what are the mechanisms of separation? So cyclone mainly have a vortex reverser allowing the clean gas to exit at the top, while they usually stand alone and solid dust collect in the conical portion of the cyclone for removal. Larger or heavier particles, the quarks, are thrown to the side and it slides down to the bottom where they are collected. So the remaining air or liquid or find reverse direction and spiral down up the center of the cyclone and is collected up. So that is that about that. Then, what are hydrocyclone? Cyclone is when you are dealing with someone is calling me. Because they changed the timetable, or we didn't know. It was now we discovered that changed the timetable. Last week we had a lecture here, but just today we hit. Don't worry, we can connect to you. Don't worry, it won't be like this. I'll check it out. Yeah, I'm so sorry. We are safe today. Next week we go to that J12 or whatever it is. So we have the hydrocyclone. Before, the difference between hydrocyclone and cyclone is because we call it cyclone because we are dealing with solid, right? But when we have hydrocyclone, it means what we are dealing with what? Liquid and solid. So for this class, it will be based on let's just limit ourselves to what? Hydrocyclone. That is the one involving solid and liquid, or liquid and gas. I think that's okay, right? Okay. Now, hydrocyclone is an analog device to separating particles or solid from what? From liquid. That is the reason why they are called hydrocyclone, or you call it hydroclones. So a hydrocyclone is a device to classify, separate or sort particles in a liquid suspension based on the ratio of their centripetal force to fluid resistance. Just like a cyclone, it's the same principle. The only thing is that we are dealing more with what? With another sample. So the ratio is I for dense, where separation by density is required, and quartz, where separation by size is required. So hydrocyclone also find application in separation of liquid of different density. Now, this is what we are saying. We can actually use it to separate solid and liquid, and we can use it to separate liquid and liquid, like oil and water. So the application is versatile because it can be used in different applications. That is the reason in most times, most instances, different most companies, they prefer the use of hydrocyclone, especially where purity is not of high importance, right? So now, what is the operating theory of hydrocyclone? A hydrocyclone operates based on what? Centripetal force. So we have a mixture of feed that enters at 90 degrees, as you can see, and it creates a vortex inside this chamber, a vortex like this. So the centrifugal acceleration separates particles or droplets based on density. So we have both centripetal force and we have centrifugal force. The centrifugal force separates those particles. Let's say we have liquid particles and solid particles. Based on what? Based on centrifugal force. But the centripetal force is the one that moves around like this. But centrifugal is the one that will dig it down. For example, you introduce your feed like this, right? Centripetal will do like this. It's more or less like you want to throw a sling. You understand? No, centrifugal has to do it down. That's based on gravity. Yeah. So now, higher density component move outward towards the wall and exit at the bottom. Now, you remember, did we do anything like centrifugal separation here? No. Okay. Now, in centrifugal separation, that's another unit operation. If, let's say, we turn this class to a system where we have bigger people here, smaller people here, right? And let's say this one, this is a rotating blade, right? Rotating everybody, right? So, once it's rotating us, the first group of people that will be rotated is the big people. So it will fling those big people to the what? To the wall. And it will come down immediately. But for some of us that are like, okay, I'm big also. For someone like Susaya, she will be at the middle like this, right? And someone like this, she will be at the middle. While all the big people were already falling from here. Do you understand now? So now what you are saying in essence is that this one will be rolling like this through centripetal force, right? But it's the centrifugal that will do the actual separation and bring you there. While the smaller people will be floating and say, please help me, until you what? Until they are separated upward. Because they are less dense. Do you understand that? Yeah. So that's just the principle. Then, okay, I think that's all. So now in in hydrocyclone separation, we have parameters. This is the reason why we are chemical engineers. We deal with parameters a lot. Even in cooking, we have parameters, right? So, and in filtration also, we have parameters. So here in hydrocyclone, we have parameters also. Because those are the parameters we need whenever we want to design this unit operation. Exactly. So one of the parameters is, okay, a hydrocyclone is a classifier that has two exits, right? We have the one at the bottom and we have the one at the top. The one at the top is called overflow, or we call it accept. Then the one up is what? underflow. We call it rejects, right? So even though we are big, we are accepted. So the underflow is generally the denser or the coarse fraction, right? While the overflow is a lighter or finer fraction, right? So now it has no moving parts and its operation depends on two major parameters. The first one is what? The feed stream, and the second one is the geometry of the cyclone. What's the meaning of this? In hydrocyclone, there is no moving parts, right? It's a force. So now, the operation depends on the characteristic of the feed stream. Are we dealing with solid liquid, liquid, or solid gas, or liquid gas? That's the first thing. The second one is the what? The geometry of the cyclone. How is it constructed in terms of angle, in terms of, because we are dealing with gravity now. So, and that is it, we have something like this conical. I don't know if you have ever seen grinder, I mean the industrial grinder before. That is the reason why it is always like this. Because we want to increase the force that is coming up. And since there are no external pump or external force, we need the one based on the what? Geometry. Is that clear? So now, so it depends on the characteristic of the feed stream and the geometry of the what? Of the cyclone. Now, what are different feed characteristics? Now, we said the parameters could be based on what? The feed stream, right? And could be based on the construction of our what? Of our cyclone. That's the geometry, right? But based on the feed stream, we have size distribution of solid in the feed stream. Now, when we have solid and liquid, we are dealing with solid and liquid. The distribution of solid, that is how dispersed the solid particles is inside the liquid, affects the what? The performance of our cyclone. And the next one is the pulp density. That is the percentage of solid inside the what? Inside our mixture. And the last one is the pulp viscosity. Pulp viscosity is just the general viscosity, right? And the last one is the inlet pressure for solid liquid separation. So all these four are the characteristics of the feed stream that what? That affect or impact on the performance of what? Of our hydrocyclone. And those are the design parameters you need to take into consideration. So now, let's assume that we don't have hydrocyclone at all. We want to design new ones. So the design of a new hydrocyclone will be dependent on the type of liquid you are dealing with. And that is the reason why a particular hydrocyclone may be used in food industry may actually not be compatible with other hydrocyclone. So a particular hydrocyclone is designed based on the liquid you are dealing with. Let me give an example. In distillation process, you discover that in distillation process, the design of your distillation column, number of train, and the rest like that will be dependent on the type of liquid or the characteristics of your crude oil. And that is a problem we have in different countries. Because most times, if you don't change the configuration of your distillation column and you bring crude oil from another country, the purity will be impacted. An example of this is that in my country, we normally have our crude oil, we send it out, right, for refining, right? And those crude oil, maybe you send it to Saudi Arabia or let's say Malta or anywhere. Their crude oil, their distillation column is designed based on what? The crude oil they are getting, right? Imagine a crude oil from another country is being exported or sent. You send that crude oil to that particular what? Distillation column. The level of what's in the purity you will get will be different. The more reason why a particular, if our crude oil is designed, our distillation column is designed based on the crude oil we are getting, we get a high purity. But by the time you send it out, it's because that distillation column is not designed based on that liquid they are getting. The distillation column they have in Angola, the design is different because it's designed based on the kind of crude oil they are getting from their country. Now we send it into that to another place. Then what happened? The purity will be different, and that is the reason most time in a particular country you discover that the crude oil, the final product you get in your own country is more purer compared to the one they're exporting outside. The reason why is that the design parameters is different. You are welcome. Sorry, it's not our fault. So don't worry, we'll finish earlier today. So do you understand now? So based on the feed stream you are introducing into your hydrocyclone, right? Based on that, let's make it difficult for them to push. Once they can push, they go back. So, do you understand now? So the design of your hydrocyclone will be dependent on the raw materials you are dealing with. The raw materials in terms of the size distribution, in terms of the pulp density, in terms of the pulp viscosity, and inlet pressure for solid liquid separation. I'm dwelling more on this because I can give you a question, a real life question, and you have to give me all these factors and expand it. You see, I didn't discuss it, so I expect you to use your own discussion, right? Don't worry, we have this video also, this recording. I'm trying to pile it up and trying to edit it because it's not well edited. So later I will upload it.
How will you ask the questions what you said?
You say what?
Like how will you ask the questions? Like what you said before.
The question?
Yeah.
You mean for the exam?
Yeah.
It's just 2 hours.
No.
So you have 2 hours to remedy yourself.
Sorry, what?
It's just 2 hours. 2 hours. For exam, right? Are you surprised?
No. I'm asking like what kind of questions, like how will you ask? You said you're not asking like this.
Yeah, what I mean is that I will give you real life trouble.
Okay.
And you will give me solution based on what I have. So now for you to figure out what I'm talking about. But it's the same example I'm using in this class.
In the previous slide, what can be this real life scenario? How can we use that slide?
You mean this?
Yeah.
I think there is a question last year. I will check.
Okay.
There's a question based on this. I will check, don't worry. I will check. Now, the second important factors is the geometry of our cyclone. That is, what is the configuration of our cyclone, right? Now, the first one is the inlet shape and area. Cyclone dimension in terms of cone angle, like this. In terms of length of the cylindrical section, in terms of the total length of the cyclone, in terms of the inlet, and the third one is the vortex and apex diameter. So those are the factors or design parameters we need based on the geometry of our cyclone. Now, design parameters and efficiency. The size at which the particle separates is a function of cyclone diameter, exit diameter, feed pressure, and relative characteristics of the particles and the liquid. So the efficiency of separation is just a function of the solid concentration. So the higher the concentration, the lower the efficiency. So it means it will be too thick. And because it's too thick, the efficiency of separation will be what? Will be lower. Then another design parameter is the cut point size. This is very, very important. A cut point size. I think I asked this question last year. What is a cut point size? And that is the only question I asked that has to do with what is. What is a cut point size? In a cyclone geometry, together with flow rate, define the cut point of the cyclone. is a measure of cyclone performance and is defined as the particle size that will be removed from the stream with 50% efficiency. That is, half the particle exit at the top and half at the bottom. That is, the particle that is larger than the cut point size will be removed with greater efficiency. Wait, it's very easy. Now, for you to pass this course, what is the cut point mark?
50%.
Huh?
50%. 59.
Is it 50?
59.
I think for biochemical it's 50, right?
For this 59.
I can't remember. I think for biochemical it's 50. I can't remember. But let's just say the pass mark is 50%. You say what? Let's say it's 50%, the pass mark. %50. Look at this. Particle larger than the cut point size will be removed with greater efficiency. Anyone getting above 50% will pass and go. But anyone getting below 50% will be what? And be retained. Do you understand that scenario? So the same thing applicable to cut point size. We are talking of cut point mark now. But we are talking of cut point size. For cut point size, when you have, like for example now, anytime you have a hydrocyclone, the first thing we ask is that, what is the cut point size of that hydrocyclone you bought for us? Oh, the cut point size is 50. No, the cut point size is 20. What this one, if the cut point size is 20, it means, you say what? Okay. Can you explain that to me? Let's say the cut point size is 20. What does that mean?
Below will be 20%, below will be retained, and the other will be at the top.
So it means everything goes. Do you understand that? Even if you fail 20%, you will still go. So that is telling you that more larger particles will be removed. So it means we want more of larger particles than smaller particles. Do you understand? But let's assume that the cut point size is around 80%. That's too high. It shows that we want more what? Smaller particles than larger particles. Don't worry. Let's move to calculation. You understand? So it means a coarse, larger cut point means that only larger particle can be separated. A finer or smaller cut point size means that what? Smaller particle can be what? Can be removed. So the higher the cut point size, yeah, it means the higher the what? Heavier particles you can remove. And the lower the cut point size, it means the lower the what? The finer particle you can remove. Okay, the higher the smaller the particle. So just in form of I don't know, I just want to find a way to explain this. It's more like, in fact, that mark, cut point mark, works well. It means if the cut point size is 70%, what that means is that it's possible that we have more failure. Do you understand? So the same thing applicable here. If the cut point size is higher, it means we have more of what? Smaller down, and lesser will be what? Larger particle. I don't know how to explain more. But wait. Don't worry, when we get to the calculation part, then you understand better. So now, we have this advantage and disadvantage of a hydrocyclone or a cyclone. The first one is that we have low capital cost. I think I mentioned it, right? Like most times they use it in place of filtration because this is versatile. You can use it in solid liquid, liquid gas, and so on and so forth. And this next one is that high efficiency. And lack of removing parts reduces water. Since it's the same thing, just pour water and clean it. You are not removing anything. You just flush it water and everything removed. But if you are dealing with filter, you will remove all the casing, remove everything before you can remove the pump, remove that and that. So for this one now, there is lack of what? Moving parts. So it reduces water during washing. Then continuous or batch removal of underflow require virtually no downtime, because this is just going down, pew, pew, pew. So it's more or less like pew, pew, pew. So don't worry, write pew, pew, pew for me in the exam, and then I will tell you. So what I'm just saying in essence is just that we have what? We have continuous or batch removal of underflow. So there is no downtime. So you just continue working. Then I mentioned it has versatile applications, right? They're smaller relative to other separation equipment. Then lastly, can operate at a wide range of what? Temperature and pressure. So it can withstand higher temperature and pressure. And the disadvantages is that it reduces efficiency at lower capacity flow. So most times we use it for a larger operation. So when you are dealing with smaller, maybe small scale, what's the name, operation, it's not advisable most times. So hence, for a less capacity flow, if you use it for a less capacity flow, then it means the efficiency will be reduced. And it's difficult to obtain good separation of substance of similar density. So when you have substance of close density, if the density is closer, then it means it will be difficult. An example of what is the density of ethanol? I think density of ethanol and water is a bit close, right? So it means it will be difficult to use this. But when you look at density of water and oil, right? So you can use it. So when you have a density that is too close, then it will be difficult. What will happen is that all of the particles will be just moving together, because all of them are what?
Same density.
Of the same density. So if they are of lighter density and they are close, it means everything will be removed from the hub. So if it is larger density and their density is close, it means everything will just come down. Wow. You understand? Then it cannot handle viscous flow, and extremely high velocity causes abrasive wear, and hydrocyclone cannot produce completely dry underflow. And lastly, clogging of the dust outlet is common in reverse flow cyclone. Do you have any question before we move forward?
Sir, please, about the cut point size.
Yes.
Is it like the size of the particle that you use to determine the cut point size? Like an average diameter of the size of particles that will be separated? Because I think it will affect the effectiveness of the hydrocyclone if it's based on how you're explaining.
Let's get to the process calculation. I was only using that scenario to explain for you to know that the same way we have cut point mark, the same way we have cut point size. But you will understand it better when we get to process calculation, right? So we have different industrial usage. A hydrocyclone is mostly used to separate heavies, that is every liquid, every solid from a liquid, and so on and so forth. So oil industry use it to separate oil from water. Then in drilling industry, it's also used in pulp and paper and mineral processing. So let's look at different process calculation. Okay. Let me give you just 2 minutes to rest. Then we come back to calculation.
Yeah.
Is that okay?
Yes.
Okay. Come on, let me use that opportunity to switch. Okay, let's look at the calculation part. So we have about 30 minutes more. So the first key process parameters is capacity. Capacity is the same thing as flow rate. So the volumetric flow rate, what is this? Phi, yeah. See, volumetric flow rate is equal to area, cross-sectional area of the inlet pipe, multiplied by flow velocity in the inlet pipe. So the first key process parameter is when you have your inlet pipe like this, so this area and the velocity is your capacity. Because don't forget, I told you that there are two key things to look into: the feed stream parameters and the geometry, right? So under the geometry, under the feed stream, we have the area of the cross-sectional area of the inlet pipe and the flow velocity in the inlet pipe. Now, back to the question. Forget about cut size mark. I'll be cut points mark. Now, cut size is the particle diameter at which there is a 50% probability of reporting to the underflow. It can be approximated as this. Again, cut size is a particle diameter at which there is a 50% probability of reporting to the underflow. What is the meaning of this? I'm coming. From here, we say, we have it here, that a cut point size is a particle size. Hello, please listen. Is a particle size that will be removed from the stream with 50% efficiency. That is, half the particle size, half the particle exit at the top and half at the bottom. So particle larger than the cut size, cut point, will be removed. So it means a particle that is smaller than cut points will be retained or separated. So a larger cut point size means that only larger particle can be separated. So a lower cut point size means that only smaller particles can be what? Can be separated.
So cut point is basically what it is, the diameter or something, or what? Like
It's more like a diameter.
diameter.
Take for instance, let's say we have let's say diameter. We were told that the diameter of this is what? Let's say 20%. Because most of the time they don't give you in terms of diameter, they give you in terms of percentage.
So like the percentage of the whole cyclone.
The whole cyclone. That's the issue.
So like if they say is that 20% of the cyclone and the cut point is 20%, then it means almost 20% of the diameter of the cyclone, right?
I'm coming, please. There's a way I explained it last year, and it was so. Maybe it's because I use cut point mark, or whatever it is. Now, I'm coming, please. What is the definition of half-life?
Half-life?
Yeah.
The time after which the particles will be reduced.
No, not particle. I mean half-life. The normal half-life we know in nuclear chemistry. What is half-life?
Yeah, the time it takes to reduce by 50%.
No. Half-life, not based on cyclone now. The half-life we know in nuclear chemistry.
Yeah, that was.
Time taken for the 50% of emission of the
time taken to maybe to
Yeah.
decay or something.
To decay. Half of what?
Half of the
Initial concentration.
Yeah,
Now.
The initial
half to
concentration.
get.
yeah, half to
Let's
get
call it
after
half.
which time it will be half of the initial concentration.
Okay. Now, let me use that as.
Okay, sir.
Okay.
Is it it like half of the original, like the amount of the substance itself
Yes.
that it takes to decay?
Yes. Now, in relation to cut point size, is given in terms of diameter, right? And let's say the cut point size is 50%, is 20%. Now, what you are looking into is that at least, even we can use the principle of cut point marks too. If the what's the name? If the cut point mark for, let's say, advanced separation process, for example, let's say it's 40 marks, that you need to get 40 marks. That doesn't mean that you must get 40 marks, right? What it's telling you is that for you to be released from here, you need to have anything above what? 40 marks. Do you understand? So the most important thing for you is that you should not have below it, right? So that is 40%. But what if the cut point mark is 90%? What does it symbolizes? It shows that you need to have at least anything above 90. So if you have 95, you are okay. But the most important thing is that it should not be below 90. So the next question that comes to mind now is that when we have higher cut point mark, what happens? It means more people will fail than what? Pass. I'm just using that one as an example. But when we have lower cut point mark, it means more people will pass. Why not many people will what? Will fail. So let's now use that one as just as a template now, based on what we have here. Larger cut point means that only larger particle sizes can be separated. It's more or less like the opposites. Do you understand what I'm saying now? So now what this one is saying is that when we have higher cut points mark, when we have larger cut point mark, it means only larger marks we go. You understand? Yeah. But when we have lower cut point mark, if we have lower cut point mark, it means lower mark.
Yeah.
No, it means, oh God. Yes, I'm just trying to find a way to explain that. Can someone help me out?
Yeah. When you have,
it's tricky, right?
no, it's simple. When you have a larger cut point mark,
Yeah.
it means that larger points will pass. But when you have a lower cut point mark, it means that both large and small will pass.
No,
No.
small will retain. Small will pass.
Small will be retained.
No, small will
Small
be
will
large.
decay, but the small
If it's
size
large,
will
but
Percentage will reduce.
Okay, let's take it this way.
Large won't pass.
In terms of hydrocyclone, when you have higher cut point size, it means only larger particle will be removed.
Yeah.
Larger.
Yeah, yes.
When you have lower cut point size, it means it's only used when you are dealing with smaller particle. Only smaller particle will be removed. Just take it like that. Susanna, sorry. Don't be tired of me. So let's just take it like that. Let's not use cut point mark as what's the name? As an example. You understand? I'm just looking at a point where cut point size is more or less like the point that separated lower particles from what? Larger particle. So it means when you are dealing with larger particles, you want more of larger particle in your what's the name? operation, it means you will order for an hydrocyclone with higher what? Higher cut point size. But when you are dealing with what? When you are dealing with what? Smaller particles. You understand? Let's say the smaller particle you are concerned about, or the less dense particle. What happened? It means you look for a cut point size is a value. A cut point size hydrocyclone with a lower what? Lower value. Do you understand now? Lower, larger, larger particle. Smaller cut point size, smaller particles.
Yeah.
I think that makes sense like that, right? Please don't confuse yourself.
If we have two cyclones, can we just like separate, like by just seeing these two cyclones, can we just tell which have the larger cut point and which have the smaller cut point?
No, it is part of specification.
Okay.
So most of the time, what determines because for example, by the time you want to design your hydrocyclone, one of the most important parameters is what? Is your cut point size. And that one falls under your phase ring. What kind of diameter of the particles are you dealing with? So the diameter of that particle will determine the cut point size you are ordering.
Depending on
If the diameter is smaller, if the diameter you are dealing with is smaller, then it means you will deal with the what? Aha, I remember now. Now, if you have a sieve, right? If you have a sieve and you are looking for a smaller particle, it means you will look for a smaller diameter sieve,
yeah.
right? But if you are looking for a bigger particle, like my head, what happens? You look for a filter which larger. Do you understand now? Aha, I think that makes sense, right? So now, so another parameter is the pressure drop or capacity. And this is the formula for pressure drop. So we don't have time to be proving this, right? But this is just a formula that shows the relationship between what? Between the Q, which is the flow rate, and the pressure drop and diameter. So delta P is the permissive pressure. So the capacity formula is now this. Don't worry. When we get to the calculation part, you will understand. Now, correction factor. Now, the correction factor is used when you want to adjust the cut point size. Let me give an example. Let's say you have an operation, right?
What?
Let's say you have an operation, separation process that require cut point size to be 20%, for example. But the supplier sent you a cut point size. You discover at the end of the day that that cut point size is not the appropriate one. Let's just say that sieve you have, as an example, is not the appropriate diameter you need. Instead of sending it back, you can actually use correction factors. Or, let's say you bought an hydrocyclone as a refurbished one, used hydrocyclone. That hydrocyclone is used for another operation separation process before. But you want to adapt it to your process. And let's say the cut point size is a particular size, and you want to adapt to your process. So you need to add a correction factor for it to work for you. And there is a formula for that. So the correction factors are adjustments to the what? Cut size in a hydrocyclone. These factors account for variation. Please listen. Account for variation in operating condition that differ from the standard assumption used to calculate the base cut size. So the design hydrocyclone you are saying have a particular cut point size, but you want to adapt it to your process, then you can use a correction what? A correction factor. So a correction factor actually fine-tune your base cut size calculation to ensure accuracy under a real-world operating condition. Do you understand me now? let me give an example. Now, let's say in most university, you apply for masters, let's say in chemical engineering, but your what's the name? Your primary course of study, let's say, is food engineering. They will ask you to take some prerequisite courses, right? Just for you to level up with the class. Huh? It's more or less like a correction factor for you to level up with the class. The same thing applicable to cut point size. You have a particular standard supplied to you, but you want to adapt it such that there will be accuracy. Then you add the correction factor, and there is a formula for it. So there is a correction factor for different parameters. The first one is that there is a correction factor for feed concentration correction. Let's say from the hydrocyclone used before, there is a particular amount of solid in the mixture that they are dealing with, but your own is lesser. So you need to add a correction factor, and that is the formula for correction factor for what? For concentration. That is for viscosity. That is 53 divided by what? 53 minus V. That V is the what? Is the volume. That is the volume of solid in the what? In the feed. This is what I'm saying. There are different parameters in hydrocyclone. Some of those parameters are feed stream based. Some are geometric based. You understand? But when the correction you need to make to your process is the correction based on the feed stream, your raw material, then you use this what? Correction factor. But let's say the correction you want to make is a prior drop. You discover that the prior drop, the rate at which your material is falling is different from what you want, right? Then that is what? The prior drop correction factor. And the last one is what? Specific gravity correction factor. This is just a formula. And at the end of the day, you will have the final cut size. So it means at the end of the day, the cut point size you will have for your operation will be different from what? The one from the supplier. Because you already introduced this. So for you now, you now say, okay, for this my process, after using the correction factor, this is my what? This is my cut point size for my process. So most times, it's not actually the cut point size from the supplier that matters. It's the cut point size for your process. And you can have a particular industry where you have different cut point size for different operations. Based on the what? On the correction factors you've added. And this is the work of a process engineer when it has to do with adding correction factor and the rest like that. Do you understand now? So, any question, please? What happened? No, we are not having next class. We have to solve this. Oh, we have 15 minutes. Oh. Okay, maybe next class I will give you questions on, because we are supposed to start another topic next class. But maybe just as we did today, we solve different questions based, I think 2 questions based on hydrocyclone. Then we can move to the next topic. Do you have any question, please? You have question?
Yeah, actually, you are making a group about the group project of this particular class.
Yes. I've not decided. That project you saw, it's possible I change it.
Okay.
So I've not decided on the groupings. Maybe next class, because I want us to do it kind of. I don't want it to start now, because this is October, November is there, and the final submission date is December.
December 12th.
To December 12th. So I want us to have a bit of. Okay, maybe next week I can. But Joseph, please remind me.
What to remind me, sir?
You are not in this class. Why?
Sorry, I was just checking.
Okay, don't worry.
Yeah.
Remind me for the coursework grouping, project grouping.
Okay,
So
sure.
I need to do it before next week.
Why not today, sir? We have 18 minutes left.
Okay, you want me to group it today?
Yeah, it will be
Is it possible? Should we do it now?
Yeah. I have to leave at 50. Sorry for that.
Is that what?
I have to leave it at 3:50.
Actually, no problem. I will group it based on. Don't worry. I can't do it now. Reason is just that I want to settle down and so that I will not miss anybody here because not all of us are in class today. So I will group it based on, no, not based on alphabet, based on how you appear on the
So just
green
make
way.
it random, no notice.
No. Don't worry, I will group in. I won't fall. I will group it based on my own. Don't worry, I will show you how we will do the grouping. So that it will not be as if I'm biased or I group somebody. So I may not group with your friends. So don't be annoyed. Because I don't want a situation whereby it is. So I want it to be an opportunity for you to know, at least meet with new people and the rest of it. Yeah. So let's look at this. Let's take attendance.